Guys, this is your educator Sujit. So this is our second part of day 7 lecture, which is loss function and optimization techniques. In part 1, we have covered the loss functions. We have seen different types of loss functions. Let's just go through them once. So we started with introducing to loss function, and then we looked to the different definitions, and then we have also looked at how different types of models require different types of losses. So we just focused with some losses like for we covered for classification problem and also for regression problem. So we have seen mean square error, loss function for regression, and then MAE, which is mean absolute error. Then we have also seen Huber loss, like which is the middle ground between MSE and MAE. And then we have seen binary cross entropy for binary classification, and then we have also seen cross entropy loss. And yeah, then we just wrapped up our lecture basically, and then yeah. So basically, we just covered the loss function and different types of losses. Like in later part of the lecture, when we get different types of model, like encoders, if we study or if we like study CNN, then like in segmentation, then we will be looking at dice score, or then we'll be looking at align losses, and then basically for different kind of problem, we'll be looking at different types of losses. So now, our next goal in this lecture is basically towards optimization techniques. So, this was the second part of this day 7 lecture. So, we will be studying about optimization techniques. Like, if we just make an agenda overview of our lecture. So, what we will be studying in this second part of our day 7 lecture, we will be looking at gradient descent. I actually hope that you already know. So, this partly will be just I will be making you this will be a revision part for you, and then we'll be looking at momentum-based optimizers, and in it we will be looking at stochastic gradient descent with momentum, and then NAG, which is Nesterov accelerated gradient, and then we'll be looking at this another out-of-the-box which is basically concept. Uh, it will be useful to study the further concepts of like AdaGrad, and then we'll be also looking at RMS prop optimizer, and then finally we'll be looking at the ADAM optimizer, and then we'll be just wrapping up this day 7 lecture part 2. So let's just go through more formal definition between of optimization technique. So basically what we do in optimization technique. So in ML or in deep learning, basically deep learning or ML problems, we what we do. Basically, we try to decrease the losses. We reach to the optimum solution of the parameters where the losses is minimum. So if you just if I just make a 2D curve of it, so let's just so what we are trying to do. One second. So suppose if this is just a basic example, like if there is a single parameter, like I know it's we already know in deep learning there are many parameters in neural networks. Like just suppose like there is a parameter W and then there is a loss. So basically what we are trying to do is like suppose the loss curve is like quadratic curve. Let's just make this as a curve, and then what we are trying to do is we have to reach this point. So we have to reach the optimum solution where the losses are minimum. So basically we are doing the same thing optimization technique for different uh, kind of losses which are dependent on different weight parameters. You already know that losses are dependent. Loss are a function of different parameters like W1, W2, different ways and biases. So it is a nested function of basically different parameters. So we have to find an optimum solution where of W1, W2, W3, etc. and bias B1, B2, B3 to to reach a point where losses are minimum. So we have to find an optimum solution of it. So the same thing we are doing in optimization techniques. So let's just read a formal definition. After calculating the loss, we need an optimization algorithm to adjust the model's parameters, weights, and biases to minimize this loss. Several optimization techniques exist, each with different strategies to adjust the weights. So the same thing which I already told you here. So basically, I can just make a 2D graph here, and I can show you 3D graph. But already know that losses are dependent on various factors, and that like we cannot imagine like 10D or 10D more than 3D. So basically, I can just show you by relating with the examples with two parameters which are dependent, basically the loss which are dependent on two parameters like a 3D graph. So you already know that they are nested function of a lot many parameters, weights, and biases. So first we'll be looking at gradient descent. I hope you already know what is gradient descent because the same thing which you must have covered in data science, your data science course. But let's go through it for one. And you already know the back propagation thing, the forward propagation, and how weight updation takes place using basically the back propagation. So let's just revise it for once again. Gradient descent. Gradient descent is the most basic optimization algorithm used to minimize the loss function by updating the model's weights biases on the gradient of the loss. So the mathematical formulation is you already know that W nu, which is the new weight, is equal to W old minus theta, which is the learning rate, and basically the gradient with the loss, gradient of the loss with respect to that particular weight. So you this thing you already know the weight adaptation techniques. You have already studied in the forward propagation and back propagation lecture. So if you want, you can just go through that lecture and revise it. These things, how the weight adaptation takes place, and we who already you must be knowing about different types of gradient descent. You must be knowing about batch gradient descent, stochastic gradient descent, and mini batch gradient descent. So, in what happens in batch gradient descent? So, in batch gradient descent, it uses the entire data set to compute gradients and updates weight. Advantage is stable convergence, and disadvantage so for large data set. So, basically, what happens in batch gradient descent? Like, if we have a data set with, like, suppose uh, if there are a data set of our same data set, which is one second. Yes. So let's just suppose that we have our same data set of let me draw. It's not, one second. Sorry for the disturbance. Yeah. So let's just suppose there is again the same data set of like house property, like price prediction, and then we have basically the area of land and the age of the house. So if I just make that thing again, just pardon me. Yeah. What? Sorry for the inconvenience. Yeah. So basically, if I just suppose that this is the age, and suppose like this, we have the area of land, area of the land, and then this is the price. The same our data set which we have been using since long time, and then we have suppose 10 rows. So basically, suppose 10 rows are there, and we have this this data set basically. So what happens in batch gradient descent that for a single epoch, like all of the data set, all of these 10 rows are passed, and a total loss is calculated, and according to that loss, weight updation takes place. So, like if we are running a model for suppose 100 epochs to train our model, so basically weight updation takes place 100 times. So weight updation will be happening for 100 times in batch gradient descent. So for every epoch, weight updation is happening one time. And what happens in stochastic gradient descent? So in SGD, it happens that our one row, basically our one row will be given to the model, So data set basically one row will be passed and then loss will be computed. Loss will be computed and then weight updation takes place and another row will be another row of data set will be passed and then another. So for every row weight updation takes place. So suppose if we have 10 rows and if we are having 100 epochs then like suppose 10 into 100. So basically, 1,000 times weight updation takes place for like every epoch, uh, 10 rows. For every, basically, we have a data set of 10 rows. So for every epoch, 10 times our weights will be updated. So this is the basic difference from for batch gradient descent. Whole data set is passed and weight updation takes place one time for an epoch. But for stochastic gradient descent, every row of a data set which when passes through the model, the weight updation takes place. So this was the key difference. And batch gradient descent, again, it is the middle ground. Like we suppose that five rows will be basically passed out of 10 rows. And so for every epoch, it will be like two times weight updation. I hope you are understanding, and I also hope that you have already studied this in data science uh, uh, lecture videos. So I just hope that you understood. So basically, why we say that advantage of stable convergence, because like you must be looking at stochastic gradient descent. So there is a very much of noise coming. You can just look at this because why there is so much of noise because every time you pass a row, a weight updation takes place. So basically, there will be a very much noise uh, because of frequent weight updation which is happening. But in case of batch gradient descent, you can see that basically weights are updated once for every epoch. So you can see that there is not so much of noise. And again, that many batch gradient descent is like again the middle ground. Why we what is the disadvantage of batch gradient descent? Again, the disadvantage of like uploading a whole data set in a memory in RAM, so it may cause the memory basically the CUDA out of memory it may cause because of the large data set. So that's why we try to break it into different batches. So that's why we got many batch gradient descent. So basically, it is the can we can say that it is more optimized path between batch gradient descent and stochastic gradient descent because we also can get a stable convergence along with no memory issue. So this is the basically the concept of gradient descent. I hope you already knew about this. So let's just move to momentum based optimizers. So I also have prepared basically we have a tool which I will give the link of these tools so you can just try it by yourself, and I also have prepared an interactive optimization visualizer so you can we can just I will also give the code of it so we can just look at them. So let's just start by studying gradient descent and momentum. So let's just suppose that maybe I don't personally know what type of gradient descent is. Let's just suppose it is a batch gradient descent and then momentum. So before studying, I want to first try to show you by this. So basically, suppose that it is a contour plot. So basically, what's happening like suppose if I try to make this. So it is a convex. So they are basically two types of loss function graphs which you will be looking at. Like it may be like convex or non-convex. So this is an example of a convex uh, thing, and then we have a non-convex graphs like this and then turns and this. So basically where we have a lot of local minima. So this will be a non-convex. So in convex we have a global minima only and no local minima. In non-convex we have local minimas and then we have like this will be a global minima and then this will be a local minima. So it may happen that sometimes by optimizing we reach to uh, suboptimum weights and biases basically. So basically suboptimum solution we reach to. And this also basically happens when we have local minimas and our updation technique doesn't work so well that we get suboptimum solution, which is not good for us. So basically, we avoid that thing, and to avoid that thing, we have different types of optimization techniques. So this I wanted to show you that this is the convex and this is the non-convex grafting, and then we have losses here, and losses, and then maybe the different parameters. So if I just write P as a parameter, so this is basically the convex and non-convex thing, which I wanted to show you. So if I say that, what is this basically the representation? Here it is like a contour plot where the outer lines are in higher altitude and then the lines going. So it is uh, like a semicircular thing. So like a semi-sphere. So let's just suppose it has to be a semi-sphere, and this is let's just suppose it is a semi-spherical. Yeah. So it is like a cup thing, which I am showing you. So it is this. So we are looking at the top of it. Like this is our eye, which we are looking from. So I hope you understand this thing. So we are looking at, I hope, personally hope that you already know about what is contour plots. So I can say that this is basically the depth of it, and then we are reaching at the higher altitudes as we go outside. So this is a convex optimization thing, and we can say that because of MSC, basically the quadratic nature of MSC, we can get these graphs. You already know because of quadratic nature of MSC, we already have this kind of graph because you already know that it is y hat. So this graph basically we get to because of quadratic nature of the loss function, but actually the loss functions are not quadratic; they are very much complex. That's why we get non-optimization types of graphs. But for studying purposes, we are taking simple graphs. We already know the graphs will be very much complex with different types of loss functions. So let's just look at this convex graph. So this is the quadratic convex. You already can see, and then these are the starting points. You can see like when I am clicking on different area, the starting point is changing, and this is basically the starting point. We can also change it from here, and then we have different optimization algorithms. So we can like just clear it and reset. So we can reset to get different types of optimization. So basically, first I will start with the gradient descent, and we just put the basic learning rate, max iteration, and animation speed. So if I just try to increase the animation speed, yeah, you can also look at different, it is given like function types. So basically, we are having a quadratic, and then we can look at Rosenbrock and then non-convex Himmelblau and different types of basically. And one thing more which I want to tell you, like this star is basically the global minima. So it is like a cup in which the center point is basically the global minima, and then we have Rosenbrock. Again, here is the global minima and different types of basically. If you, I just try to open this, so yeah. So you can just try to look at different types of functions and their graphs. So you will get like this if I open. So you can just look at different the more 3D visualization of these graphs you can look at. So let's just go to it, and if we start with the quadratic one, and if we just use the gradient descent, then just if I try to run, then you will look at how many iteration and basically gradient descent, and then how many iteration it took to converge to the global minima, and then you can see that the final value. So basically, it's lying on 0 cross 0. The global minima is at 0 cross 0, and distance to optimal, then we can also look at final value 0.01. So the final value of our solution, you can look at it is around. So basically, the gradients became so small, so it is hard to converge that. That's why it's 0.001. It has not converged fully because you already know that gradient becomes so small. The curve has become so flat that the gradients are becoming so small. So what I personally means that if I say what is happening is like W new is equal to W old. So this is our rate and meter times tau by tau W. So what's happening is that tau by tau W basically is very small. So it's approximately equals to zero. So this whole term will be approximately equals to zero. It's very small. So after subtracting W odd by W basically W odd by neta dl by dot W. So it's not giving any better weight. So that's why it's becoming tough to converse. That's why we are getting some final value. So basically, this I wanted to show the gradient descent part of this. And if I just try, you for now you don't know about momentum, but just I want to show you how the things are working. So if I just try to reset and then only momentum and gradient descent, then you see that how fast momentum is basically coming. And you also saw that momentum while using momentum, the momentum first it has reached the optimal solution and then it just tried to pass the optimal solution and then it just tried to come and settle down. So basically you can see that there is a kind of certain oscillation which is happening. So if I just try to show you by this graph also, so if I just still select a global minimum thing. Like this graph is basically the same thing here. So if I just try to show, just follow the momentum, the this one basically, and if I just restart it, you can see that it is coming and it is settling down. If I just try to, I will be telling you more about the decay rate. So if I just try to make it this. Basically restart it and you can see that the same thing is happening basically. So when a ball of momentum is coming down, it's just oscillating. So the same thing in contour plot, you can see that if I just again try to run, see, so this is the top view of basically the old that 3D visualizer. So you can see if I just remove these basically RMS Prof, Adam, and I don't know what this right thing is basically. But if we just follow gradient descent and momentum, and we just restarted, you can see the same thing is happening in 3D, like the same you watched in Contour Plot 2D. So basically, you can see that momentum in this case conversed faster than gradient descent in this case, basically. So if I just follow the so momentum just took 37 iteration and it has conversed, but gradient descent took 200 iteration to converse. So in this thing, we can say that momentum proved better. So let's just go through the theory of momentum, and then we will be then we'll be looking more at what's happening and how this thing is working. So let's just read the definition first and then try to understand. But look, let's go first. What I want to tell you the concept of momentum first. So if you just follow this thing, you must be realizing if I say that. Suppose this has to be a ball. Suppose this as a physics scenario, and you are taking a ball. So suppose that there is a gravity downside, and why? So suppose that it is a gravity downside, and just remove the gradient descent thing also. So a ball is coming downside a slope, and it's settling down. So if you just try to understand by physical nature of it, so you must be understanding the physical nature of the ball when there's a gravity downside. So suppose that this is it is coming down. So this is a cup thing, the same convex thing, and it is coming down and settling here. So before settling, it also oscillates a little. So if I just try to make it in an enlarged version, let's just suppose it to be a cup, and then there is a ball. So this ball is first coming down, and again coming down. So suppose this is a physics problem. You already must be understanding the conservation of energy formula. So if I just suppose that it is basically coming, so this is the height h, and then gravity is coming downside. So this is the gravity, and you must know that it equates to basically the change in kinetic energy. So kinetic energy final minus kinetic energy initial. You already have started with zero velocity. So final velocity will be something like this. So basically, you have a v velocity here. So because of this v velocity, it will again go up, and then it will be oscillating before it settle down. So it will be oscillating from then to this and then this. So it will be settling down. So the same thing is happening. So momentum can be compared with the the momentum from the physics thing. So this is basically the same thing happening here. So now you just got a basic idea of what's happening. So now just we should just go through more formal definition of it. So stochastic gradient descent with momentum is standard SGD can oscillate and converge slowly. So you already saw basically that standard SGD is taking 200 iteration to converge, but the momentum did very fast. So you can say that momentum accelerates convergence by accumulating gradients from previous steps. So this is a very important like that line that momentum accelerates convergence by accumulating gradients from previous steps. So here is the momentum formula. Sure, the momentum update from formulas written similarly. Basically, this is the prompt I gave. So basically, just remove this thing. So this is our formula of momentum. So this is the weight updation formula you already know. You know about just suppose theta t to be w new. So basically, theta t is the parameter, and we are supposing w to be our parameter. So it's just the same thing. So theta t or wt is basically the current or new weight or new parameter, and the older one wt minus one. So it is for older one, and you already did neta, and then we basically dou by dot. So gradient with respect to that parameter. So again, the same what we have done is that we replaced this thing with VT. And what is VT? So what is VT? Sorry. So VT is here it is written as VT is the velocity momentum term at step t. So VT is basically VT can be considered as the velocity, the same velocity that we can take like from physics, and basically VT is the velocity at step t. So basically now we have changed this whole term with VT term here. So what is VT? Basically the formula of VT. So the formula of VT is equal to beta VT minus one plus alpha delta, basically the gradient with of loss with respect to. So J is basically L, and I hope that you won't be suffering with annotation. So basically, if I just try it, so to suppose this as W, because we are considering it as W, and consider it as meta, which is the learning rate. If you just try to read the explanation part, you won't be getting confused with the annotation. So this is basically the gradient of the loss function with respect to the parameter theta. So you already understand what the thing is going on. So Vt is basically beta. Beta is the momentum coefficient. We also called it as decay rate, and into Vt minus one plus alpha. So this thing you already know. This thing is same as this thing. So what changes have occurred here, that we are adding one more term here, beta Vt minus 1. So basically this is happening that in momentum we are adding this term alone to create the formula of momentum. It's just wait for it to get updated. Yeah. So I hope you got the idea what is happening here. So in our original gradient descent, we used to have only this formula, but in momentum we are adding this term. So basically Vt we are subtracting theta t minus one minus Vt. So our weight updation, basically the Vt is a whole part of this thing. So the same thing is written here, and the same thing I wrote here in more constructive formula for better understanding. And why it is said that momentum accelerates convergence by accumulating gradients from previous stage. So let's just try to understand what this line wants to say. So what's happening? Like suppose it is our t is equal to 0. So at step 0, so v0. So in many places v0, basically we consider v0 to be 0. So if I say so we consider v0 to be 0, and if we just try to calculate v1 and then just try to go on. So if I try to calculate v1, so v1 will be like v1 plus beta into v0. So v0 is 0. So not just let's just not write it and consider it alpha, which is our learning rate, alpha or meta, which you already know, which the conventions, annotations we are considering. So loss and theta 0. So basically, if I just try to again make the same graph, like so this is like the side version, the 2D version of it, and just suppose that there is another parameter. So again, it is the same. Uh, again, this is the same thing, which is in basically the cup thing in a 2D. Basically, here we are showing try to show it in 3D by making another axis to it. So let's just suppose v0 0, and then this is theta 0. So this is our theta 0 we have written, and then v1 will be used to calculate. Basically, v1 will be used to calculate uh, uh, theta 1. So basically, theta 1 is calculated using the formula, and suppose that theta 1 is somewhat here. Okay. So now let's just calculate v2. So what will be v2? So v2 will be again, sorry for the glitch. If I let's just add one page to it and then just try to cover this in more detail. Yeah. So let's just try to cover this in, the page got added in the wrong place. So just try if I just try to add a page to it. One second. Yeah. Now, now let's understand this in very detail. So what's happening? So it's happening like if we are just first draw the uh, first draw diagram. So suppose this is our convex function, the same function which you have been watching, and just draw it a little bigger for more better understanding. Yeah. So this is our convex function. And suppose that we are for using the optimization, momentum optimization technique. And let's just suppose that we are starting from this position. So basically, this is our uh, position from the random position, like suppose it like theta or W. So basically, or W, we are taking it, or W. So it is or. So we are considering theta or W as our parameter, and then we have loss in this axis, and just the random initialized value of theta or W is like suppose theta 0. And then what's happening? So basically, we already know that the formula of Vt is basically beta Vt minus 1 plus alpha. Basically, alpha is our learning rate, and then gradient with respect to that parameter at that position. So what's happening is that if we calculate V1, so beta V0 plus alpha or neta as a learning rate, and then J. So basically the loss will be calculated. Basically, the slope of that will be calculated from this point. So suppose the slope which is calculated, and we just don't want to go to it. You already understand what's happening. So you already know that V0 is zero. So we can say that this whole thing will be zero, and we can say then that updation will happen. So basically, if I just go to and read the formula, so suppose that theta 1 is equal to theta 0 minus Vt. So Vt is alpha G theta 0. So this the for the first iteration, so it is similar to our normal uh, SDD or batch gradient descent. So it is the same. But now what's happened? So let's just suppose that in initial also we take our velocity as zero because we already know that we are not giving any velocity to this piece of block or mass m, and so it's on basically. We are not giving any velocity to it. Just with the same analogy, we can say that our v0 is zero. So for the first iteration of our step, it is basically the same formula as SGD. But now what happens with V2? So for V2, if I say V2, so for V2 is equal, V2 is beta V1 plus alpha V theta. Okay, so basically, again, the slope will be calculated from the theta 1 position. So if we mark, like, suppose after weight updation, so the theta 1 comes to be here. So the gradient will be calculated from this position, and beta V1, we already know that we will put this value. So V2 is equals to beta alpha theta theta plus alpha theta. So basically, we got our V2, and the same weight updation will happen. Now, we will put the same formula will follow to get the weight updation, and now you can see the factor of basically, if I just again write for better explanation, so theta 2 will be theta 1 minus beta alpha, the slope of at zero at theta 0 minus alpha theta, the slope as at theta 1. So now you got another position of theta 2. You can look like this factor. If you have used our original SGD, then you will see that only this factor would have come. Like if you were using the SGD, then what you have done? So basically, you have just took the theta 1 of this place and then the slope of at this point multiplied by its learning rate. So that is theta 1 minus that the slope of this theta 1 place multiplied by learning rate. But now you can see when momentum, we are considering our optimizer as momentum, then you can see that this another term, which is the slope of this gradient of this position theta 0 multiplied with some beta term has come. So again, if we try to calculate again a theta 3, so if we try to calculate theta 3, so I'm just directly writing it, theta 3 will be is equals to theta 2 minus alpha theta 2, and then basically minus beta. The gradient or at theta, beta square theta 0. So you can follow like if original SGD if we are taking, then it will be just like theta 2 will be the slope, theta 3 will be equals to theta 2 minus slope at gradient at theta 2. But you can see that the previous slopes are also, previous gradients are also contributing in the outcome or the parameter updation. So the same thing is here. So with every new weight updation, the previous weights slope of the weights are contributing basically, and if they are contributing a little lesser. Like beta is actually beta term is between 0 to 1. So you can look at like beta values between 0 to 1. So every time like beta square will be lesser than beta and beta cube will be lesser than beta square. So you will notice that as we move further, the our beta basically the slope of previous weights or previous weights become lesser prominent or lesser contributing as we are multiplying it with a beta whose value is between 0 and 1. So it will be it will be weighing or providing a lesser, making it possible for weights, the previous weights to contribute lesser in a new weight updation. So basically, beta square, it is multiplied j 0, theta 0 will be weighing or contributing lesser in theta 3, and it will more contribute more lesser in theta 4, and similarly the pattern will go on. So in theta 1 calculation, the theta 0 gradient was contributing very good amount, and as soon as we reached to theta 2, it contributed lesser because beta was multiplied to it. And in theta 3, you can see that theta 0, which is the initial weight, the oldest weight parameter, the initial weight parameter is contributing lesser. And if we continue this loop, like if we try to go on, like in theta 5 or theta 6, then the contribution by theta 0 will becomes more smaller and smaller, and same pattern will go for theta 1, theta 2, and it will be getting smaller and smaller. So the same thing is written that momentum accelerates convergence by accumulating gradients from previous step. So now you can see that in theta 3, if we were using simple SGD, then only these terms would have come, the term here which is written here. But if we are in momentum, the previous gradients are also contributing, although their contribution is getting little by different, getting smaller by further steps, but they are contributing. That's why we can say that momentum accelerates convergence by accumulating gradients from previous steps. So this is the whole concept of momentum. So I hope you understand what is the concept behind momentum, and if I also made a, let me check it once. So basically, I made a collab book also, and you can just so basically this is not very much of use. So basically, you can see that the losses are getting minimum earlier because there is no comparison with SGD, so I cannot tell that. Whether it is comparable with basically I cannot say that the convergence rate is faster. So basically, if we just look at this and if we run it again, and you can see that, yes, you can see that it converged in just 37 iteration. It has reached to its global minima. But if looking at gradation, you can see that it is taking, still it is taking time. Still it is not converging. So basically, we can say that momentum, by using momentum, we can converge to the solution very easily, very faster. So that's why momentum can be very helpful in getting, basically, we are getting the speed, we are adding a speed to our weight updation. So momentum is basically, this term is basically the speed which we are adding to our weight updation technique. So this was the whole topic of momentum, and basically the advantage of this whole thing is that it accelerates convergence in inconsistent direction, reduces oscillation in inconsistent direction, and helps escape shallow local minima. So let's just look at another. If I say there was no, let's just try and looking at this thing. So if I say, if I just change to local minimum, and if I just add
gradient descent also. So restart it. Now look. Now look what's happening. So here it is a local minimum and here it is a global minimum. And so what's happening? Let's just reduce it's like restart it. Now, what had happened? So the momentum is also the blue one ball is basically of gradient descent and the basically what the magenta color is of momentum. So what's happening? Like they all are getting stuck at the local minimum. So this will be giving a suboptimum solution, but we have to get an optimum solution. So we have to reach the global minima. And what is happening that both of our optimization techniques are getting in the suboptimal solution. If we increase the decay rate, you already know what is decay rate, beta. So beta will be increased. So you already know the beta is directly basically it's helping our weight updation technique by more value, giving a more value to it. So weight updation will happen more faster. So if we just increase that thing like 0.5 and learning rate is same for all and restart. You can see it just escaped the local minima. It just escaped the local minima to reach the global minima. And that's the same thing written in that line. If I read it one, helps escape shallow local minima. So this is the basically the key advantage of our momentum is that it helps to escape the shallow minima. If I just show you again once, you can just see. If I start from this is the new starting point, you can just see it just keeps the local minima to settle down in global minima. Although the convergence is a little slower because of the oscillations which are happening, but yes, it is getting to the local minima to give us a give us an optimum solution. So that's why it is the key advantage of basically momentum based optimizers. Now, let's just again try to understand. Let's just try to first get the idea of Nesterov gradient descent before getting into the concept of Nesterov gradient descent. And then it's better to first understand through the graphical part, through the visualizer, and then just go through the theory. So if I just on gradient descent, if I just try to, yeah, Nesterov gradient descent, and just run it. Just follow the balls. If I just try to decrease the animation speed and again run them. So the lighter blue ball is basically our momentum, and the a little darker blue ball is our next drop. So you see the oscillations in so basically here Nesterov is also giving not giving a perfect solution. So I don't think whether what is happening at the back end. So let's just try in this. Basically, it's more accurate, and let's just try. So oh, I don't think they have given. What is this? This is Nesterov. Let's try it by running. Let's just. No, no, it's just it's nothing. So you have to understand by this as well, this only. So basically, if I just try to change the position little and just try to run it, you can see basically that Nestor and Momentum are performing. Basically, they are performing like closer to each other. What I'm looking for is basically that what happens, let's just try to understand. What's happening that if you follow the lighter blue version of the ball and the darker blue version, which is NHC, Nesterov, what's suffering from accelerated gradient. So basically, what's happening that you can follow that momentum is like the ball is going more further away than coming back, and you can see that if I just play this momentum thing, so suppose that if I just restart, so suppose that if the ball is coming from here, it is going farther and then it's coming a second down. What will be happening with Nestrov is that it will also come from here. But what happens that it will not go more further. You can look again from this thing. So you can follow that momentum ball is going further, but Nesterov is not going further, and they are approximately settling down to the same number of iterations. But actually, the Nesterov is better because it settled down earlier. So I don't know why it is happening. Maybe the backend thing is working, and it is giving better possibility for basically momentum and not for Nesterov. So let's just try to change the graph. And let's just try to, yeah. Oh no, oh no, oh no. It's just too tough because we cannot increase the scale of this graph. So we basically don't know what's happening inside. So I just try I just try to, yeah. Yeah. Yeah, here you can understand. Like, see, what just happened is basically, so if I just, yeah, very good example, very good. So this is our curve of Himmel-Blau. So if I just try to, uh, yeah, so this is our Himmel-Blau function. So the same thing from the top version we can say is the contour, and here we can say that it is uh, a global minimum. So basically this and they here exactly we are keeping our initializing our basically the parameters and if just start so if I just start it you can see that the dark blue momentum is escaping the global minimum. It may happen that momentum because of its speed from accumulated gradient may escape the global minimum. It may happen because of the oscillations. So the oscillations are so fast that it may escape the. So if I just decrease the animation speed and run it again, so you look at it just escaped the global minima to settle down in local minima because of its exceeding speed, because of its oscillation. So sometimes we need to damp the oscillations. So what we mean by damping the oscillation that we have to decrease the oscillations which are happening so that our momentum does not exceed or does not come out of the global minima to settle down to some local minima thing. So this basically this loss, basically this Himmel-Blau function shows the same thing. So if I just try to run it once more, if I just try to run it, you can see NAC settled down with the local minima, with the global minima. You can just follow it. The darker blue line, the NAC settled down here, where the star is basically the global minima. But our momentum basically traveled, it came out of the local minima, basically, sorry, pardon me, it came out of the global minima to settle down in local minima, and then it just took 200 iterations to settle down. So basically, we in NAT, we basically want to damp those oscillations. If I just again try to go to the quadratic part, and if we play it again, you can see we have damped the oscillations while using Nestrov. So basically, this is the whole idea behind it. Like if it may happen that because of momentum, we reach to basically we breached the global minima solution to reach a local minima. So we just try to use a damper called basically we have adding a damp or we are damping the this thing our movement so that we can settle down with the global minima and we just don't cross the global minima to settle down in more further local minima. So this was the whole concept behind the Nesterov accelerated gradient, and let's just look at the basic what changes in the formula we did to better understand what's happening with the formula and how we did this whole thing. So Nesterov accelerated gradient energy improves upon momentum by computing gradients at the lockhead position, providing better anticipation of where the parameters are heading. So key insights energy computes the gradient. So this is the basically the formula, and then rather than at the current position. So more responsive to changing gradient direction often converges faster than standard momentum. Acceleration often converges. So we can say that. this time which we are looking at didn't converge faster than it, but it often converges faster than standard momentum because the standard momentum wastes many of its more of its time in damping. So basically in oscillating, so it takes more time to converge. We basically in this convex function we basically don't know the what is the shape of that convex, so we can't say that why momentum is because we have to try different optimizers to know which is working better. So we can't just say that every time it will converge faster than momentum. Sometimes maybe momentum converges faster than NAG or Nesterov accelerated gradients. So a better theoretical conversion guarantees. So what changes in the formula is I just don't want to take you into the formula. I will try to make you understand through it. So what's happening in momentum? So what's happening in momentum? Like if I just suppose that we are in theta one position and then what we are doing is basically we are just traveling. So there is a momentum term and then there is a gradient term. So we can just say that this is the momentum term we associated with it, velocity associated with it, and then the gradient term. So for theta 2 calculation, what did we do? So let's just say theta 1 calculation, what did we do? So for theta 1 calculation, we just theta 0 minus gradient, and then theta 2 calculation, we basically what we are doing till now. So we are taking a velocity component. So this is the velocity component, and we are taking the gradient component. So if I just say what we are doing in V2 calculation, that we are taking a velocity component and a gradient component. You have been taking gradient component since long, but we are also considering velocity component when we consider momentum. You already understood this part. What we are considering? We are considering momentum component with gradient component. Gradient thing you already are using since long with different types of gradient descent techniques, but we are also considering momentum consideration. So now what's happening? So let's suppose that we are at theta one position and we have to do a weight updation. So what's happening? That we calculate the velocity from this part and also the gradient, and then we just move to theta two. But now what's happening in Nesterov gradient descent? In Nesterov gradient descent, we first calculate the velocity and just try to move someplace, some random place, suppose it. And then we calculate basically our gradient to that location. So consider it as pseudo location, and then we calculate look at we also say as the look head position. If I just yeah, we also say at consider it as look at position, and then from that position we calculate the gradient to get to some position. So if I say that the slope will be lesser, so basically we will be landing up at somewhere here. So this is what happens when we consider a Nesterov gradient descent, accelerated gradient basically. So what we are doing basically we are taking a velocity component jump earlier and then calculating the slope at that position. Earlier in momentum, what we used to do, we calculated momentum and gradient at that same position and take a total complete jump. But what we are doing in NAG is that we are taking velocity jump first and then calculating the gradient at that position we have reached because of that velocity. I hope you understood this thing. So basically, this is the whole concept behind it, and you can just look at that how we are doing. You can just go through the formula and you will understand. So the look at position, as I already told you, that we are going at a look at position. It's considered as a pseudo position, and then from there we are calculating the gradient to get to the our updated position. So this was the whole concept behind stochastic gradient descent with a momentum, Nesterov accelerated gradient. And now we will be going to our next concept of exponentially weighted moving averages. So let's just go to another concept of exponentially weighted moving average. It it is just a concept which I want to tell you before we go to another optimizers technique like RMS prop or basically Adam, our most famous optimizer. So before diving into advanced optimizers, it's crucial to understand exponentially weighted moving average as they form the foundation of modern optimization algorithms like Adam and RMS prop. So what is EWMA? An exponentially weighted moving average gives more weight to recent observations while exponentially decreasing weights for older observations. This creates a memory that focuses on recent trends. So unexpectedly, I just told the same thing which we studied in momentum. So the same thing is being taught here also, that when we move forward and we move further, we are giving lesser values to the old, lesser weight to the older values. So the same thing is told here, that as we basically as we move further, we are moving further, and exponentially weighted moving averages give more weight to recent observations while exponentially decreasing weights for older observations. The same thing is like the newer will basically get more value because no beta is multiplied with it, and with as it become older, betas are multiplied. The D rate is basically multiplied with it, and it is decreasing the weight of it. So the same thing is EWMA. And for the understanding, if you have ever looked at forecasting data, the weather forecasting data, or have you ever looked at the stock market price data? So you would have you would have known that it is a spiky data with changing trends of prices, or if we are using the forecasting data of temperature, then changing trend of temperature, hourly change, or in stock prices, you can see second changes in seconds. So it is a very spiky data. So this again, VT, you can consider it as a velocity, but here it is written as it is the exponentially weighted moving average at time t. So the VT is basically that there we consider it as a velocity, but here it is the exponentially weighted moving average, which you will be calculating. And theta t is our input values. So theta t is the current observation, analogous to xt in standard EWM. VT minus one is the previous EWM. And you can look at VT minus one is that previous, and if we calculate VT, then in VT plus one, we will be putting it at here, and then again beta will be multiplied with VT minus one. So it is somehow getting decreased, and beta is the smoothing parameter or decay factor. So I hope you understood what is the basic concepts. So I just don't want to go in detail because you already have looked it. So if I just I already made this. So if I just reconnect it, this whole thing basically this collab book, I will give it to you, and along with the code for this interactive optimization algorithm, which you can run on your local device. And also I will be giving this uh, basically this. The GitHub repo of this visualizer tool, which you can download and run by yourself, and you will just by running you will understand very things which are needed for better understanding. So if I just try to run this code, so let's just wait. It's running. Yes. Yes. So let's just suppose that this is our stock market price data, and let's just suppose these are our time steps in which our stock market values are changing. And so this is our EWMA. Bias corrected, I will tell you later on, but just understand it is our EWMA. So you can just look at for different beta, like beta is equal to zero point 0.1. So if I just try to uh, follow this thing, like the rule of thumb here, it is written EWMA averages over approximately 1 upon 1 minus beta observation. So let's just try to write, like if you are taking beta as 0.9. Okay. So again, no problem, no problem. So if I just do 0.9 and 1.0.1 to 10. So this basically this formula tells that it is the average over last 10 observations. So like if I just try to alter the values of beta, so where the beta is given, yeah. So it is already zero point 0.9. So basically, if we are standing at this position, So it is the average of last in observation, approximate average of last in position. If we are here, it is an approximate average of last in observation from this position. So if I just try to do it like if I try to like use beta as 0.1, let's just take not 0.1, just take it 0.5 if I say. So 1 upon 0.5 will be 2. Yeah, 2. So it will be the observation of last two average approximate average observation of last 2 days, last previous days of previous time steps. What we are basically considering in x-axis. So if I just try to alter this thing and then just try to run this, yeah, you can see what you have noticed, what you have noticed. And again, if we just try to take more values to it, like so, what will be basically? One second. So it will be approximately something 1.1 something. So if I just try to do 0.1 and then just try to, yeah, you now what you can see. So from 0.9, you got this. So basically, at this point, you have an average approximation of last 10 days. And if you just try to go to this, so at this point, you have average approximation of last 2 days. And if you go to 0.1, you have average approximation of suppose like 1 day. So basically, you are getting to more, not from more stable pattern to more noisy pattern. So that's why how beta helps it. Like if we try to get more closer, like 0.99, more smooth graph you can see. Because it will be compared to zero point 0.9, the smoothing factor or decay factor 0.9, it will give more smooth 0.99 will give more smoothness to it because it will be approximate average of more data behind it as compared to zero point 0.9. So this is basically the EWMA. So this I wanted to tell you before we move further. So you just try to change the value and try to understand and also go through the formula and try to calculate what we have done here. So you will better understand how the things are going behind the scene. So next is our adaptive learning rate optimizer or ADAGRAD. So let's just understand what is ADAGRAD and then Adam optimizer. And then we will just wrap up our this day 7 lecture part 2. So what is happening in adaptive learning rate or ADAGRAD? So adaptive gradient, ADAGRAD learns the learning parameter for learning rate for each parameter based on historical gradients, giving frequently updated parameters, smaller learning rates. So the sparse gradient problem. So there is a sparse gradient problem which occurs. So in an LP recommendation system and high dimensional problems, most features are zero most of the time. So what's happened that in NLP you will be studying like if you pass a token, then there is a fixed length of that token, and to achieve that, sometimes we have a token which have very less value to it, and then we just to make the token size to that extent we add like we do padding kind of thing, and we just add zeros to increase that size. So basically, what happens that because of zero sparse data comes into picture, and our basically the you will be looking at loss graphs. What happened to the loss graph? It's become extended. So I will just tell you. Wait for a second. If I just complete this, only a few features are active for a given sample. Traditional optimizers use the same learning rate for all parameters, which is suboptimal. So I hopefully made yeah, I hopefully made this thing for better understanding of what's happening behind scene. Let's just give some time to it to run. So did it run? Yeah, it had. Yeah, just neglect that part. Contour shape transformation circle to left. So let's just explain what's happened. So if considering it as a sparse data, like suppose there are like some data set. And what happens that in that data set, there is a row which contains some values like uh, 1, 3, 0, 0, 0, 2, 1, 5, 0, 0, 0. And there are basically sparse data, which means there are very many amount of zeros in that data feature column. So basically what happens to our graph, that our graph, basically the loss function, it automatically basically turns out to be from circle to ellipse. So the same thing is written, I think it is written here, contour transformation explanation. So original landscape. So basically the contour becomes more elliptical in nature. So what happens that if I just try to help you understand this, that because of this sparse feature, what SGD does is that the transformation, basically the weight updation takes place in one direction to a large extent, and then it just goes around and then settle down. So basically, you can see that this thing is happening, that first weight updation takes place in only one direction, and then when basically it has covered the one direction, it goes and then to the other direction to settle down. So basically, if you can see that at first only the updation takes place in bias, and then it's happening in weight. So what's happening behind the scene is that if you just know the formula, like if you just remember that Z is equal to W x plus B thing. And if we just derive that thing, so let's just take another copy and pen thing and try to understand it in better way. So this, so let's just add a page. So you already know that in weight updation, like if I have a formula like Z is equal to Ws plus P, and the weight updation which will happen is like what will be basically if I consider MSE loss, so y minus y hat whole square. So this is our loss. So what will be basically dou L by dou W. So dou L by dou W will be uh, by dou Y hat, and then basically dou Y hat by dou W. Okay. So what's happening is that 2 y minus y hat and dou I had by dou W. So considering it has to be y hat, and why considering it to be y hat? Because we are considering a linear activation function. We are not applying any activation function. The value which is coming to basically the node of but basically the weighted sum plus bias is only our value. We are not applying it to basically taking linear activation function. You already know what is linear activation. We are not making any changes. The value which is coming is statically passed. So basically, if this dou y by dou w, so it is equals to x. So you see that if there is a column of some input x where it is two zeros, 2 1 2 0 0 0 0 0, then how the weight updation will take place? Like every time it will, most of the time it will be zero. So that is what happens. Like here, if we go. that because of very input value to be containing very large amount of zeros, the weight updation doesn't take place in W direction and only in bias direction weight updation takes place. Like if again we try to calculate the gradient with respect to parameter of bias. So so it will be simply y minus y hat into 1. So if any bias term basically will happen, basically this will be 1 and when we get the answer basically, so basically there is no input factor which is affecting. So if there will be a bias term, it won't be affecting anything as there is no multiplication with the input. You already know that weights are dependent with the input. Weight addition is dependent with the input, but bias is dependent only on the node thing. It is independent of the weight. It is dependent or independent of the input feature. So basically, you can see that bias updation will take place gradually, but when the it reaches the downside, then slowly the weight updation will take place. But what happens in Adagrad is that there is a stable convergence, like both sides it's converging equally, so it will converge more faster. So basically, you can read the both theory to it, which I already added. So you just go through this theory, the sparse gradient problem, which I already added there, and it is also written here, so you can just go through the code and understand what's happening with the sparse gradient problem. So Adagrad is used to basically solve these problems for more stable convergence. So Adagrad's solution is individual learning rates. Each parameter gets own adaptive learning rate based on the its gradient history. So what happened will that because the bias term will be converging more faster, so it will get a lower learning rate, and because weight term is not converging because the sparse features where zero is coming too much, so the weight updation is not possible. So the learning rate will be increased whenever the things like one or two come, so that it can give a more stable and basically increase the learning rate of that weight parameters so that they can converge equally. So suppose that there is a velocity thing here and here. So it is the resultant of that velocity. So what's happening in there that weight here the velocity is basically the weight velocity is zero. So only the bias change is happening from with respect to parallel y-axis. But in weight side it is zero. So what I'm speaking is let's just suppose that there is a curve thing here, and what is happening is that because of like there is bias and there is weight, these are the two components of velocity, considering it as a velocity. So this is the resultant. So what's happening in sparse gradient problem when we are taking SDV, the change in this part. So this is weight and this is bias. So this component is zero. So only the velocity change, basically the gradient change is happening, updation is happening in this side. But what if we just try to increase the learning rate for the values which are in case coming, like if some other value than zero is coming, then the if we increase the learning rate, so updation will take place in this direction also, in this direction also. So there will be a resultant which will be converging directly to the global minima. So this will be very helpful than converging it and taking a longer time and different values to get and more computations. So this was the sparse gradient problem, and Adagrad solved this. Basically, the Adagrad solved this problem by taking different learning rate for different parameters based on its gradient history. So yes, frequency-based adaptation, frequently adapted parameters, smaller learning rates, more stable, and rarely adapted parameter, larger learning rates, faster learning when they appear. So basically here you can say that this is, in our case, we consider it as weights are rarely updated. So we can say that this will be having a larger running rate and this will be our basically B because it is frequently changing, so it will be having a lesser learning rate. What's happening? So this will be our bias. Perfect for word embedding will be covering and everything you will see these things. Advantages automatically adapts learning rates, work well with sparse gradients, no need to manually tune learning rate. Disadvantage learning rate decreases monotonically, can stop learning too early, and hard to convince. So we have this thing formula for it. So if you already understood the formula for basically momentum, and then this will be a very piece of cake to understand for you. If you just try to go through it once by yourself, you will just understand what's happening in it. It's just self visualization which will be helpful for you, because these things are once covered, and it's of no use trying to explain everything again and again the same thing, which that's why, because it takes time, and that is easy part which you can do. So these are the parameters, and for epsilon, which I can tell you because this thing is new for you, small constant added to denominator. Suppose that because it may happen that VT is zero, so epsilon, because V zero we consider that as zero, and so to avoid that zero thing when infinity, the possibility of that, so we take an small constant. So this I wanted to tell you. So you just go through this and try to understand. If any problem happens, then you can just comment it down, and we will try to make a video for that problem, and that will be covered. And for RMS prop optimizer, so the problem, the disadvantage is hard to convert. So when you will try to solve this, you will understand that we reach a position when gradient becomes so smaller that the possibility of converging becomes very small. So it is hard to converge. So the disadvantage is solved by RMS prop. So what is RMS prop? So RMS prop is root mean square propagation. So prop is for propagation. Is another adaptive learning rate optimization technique. It maintains a moving average of squared gradients and uses this to normalize this gradient. So basically, compute the moving average of squared gradient. So moving average, you already understood what is moving average, and you know basically how moving average thing is working. So you just try to go with the RMS prop optimizer again by yourself. The formula basically you should know the you should know the application, which will be told you in later lectures. The application of it, the concept behind is already covered, and if you go through it by yourself, you will understand it more, because by understanding, by doing the formula by yourself will be very helpful. And if I just go to the Adam optimizer, which is again a very important optimizer, and it is the most famous one. So Adam is one of the most popular optimization for algorithms in deep learning. It combines the advantages of both SGD with momentum and RMS prop. Adam adjusts the learning rate for each parameter individually based on estimates of first and second moments of the gradient. So again, it is taking the EWMA thing. So compute biased first moment estimate. So first we are calculating MT. So there are two terms basically, MT and VT. So MT is basically, so what is happening that again you will be looking at that we are taking the moment thing also, and we are also taking the bias thing. So uh, basically we are taking the gradient thing, and we are also taking the moment thing. So the same thing here, it is written GT. Basically the annotation has seen GT is now the basically our uh, gradient with respect to that parameter. So we are taking the two components, and then we are there are another B2s, another gradient, and then we are doing like the bias for moments. This mathematics behind it. You don't need to go up why we are correcting the bias. You just need to know the application part of this, and you just know the weight updation formula and what is happening. So you just go through it, and you will understand how the things will happen. So Adam works well for sparse gradient. This you have to remember. It is computationally efficient and requires less tuning of hyperparameters. So there is another piece of code which is given, and I will try to just take you to this. Yeah. So we just try to make a simple model. So this script is done in Python based, and this script is basically in TensorFlow. So this is PyTorch. Basically, we will be looking at more of it in the future. And if I just try to run, so it's running. So basically, Adam also we have covered, and basically I am trying to run and show the comparison behind them. So you can see that losses decrease faster for like SGD is the slowest plus SGD plus momentum plus SGD with Nesterov. So Nesterov losses again decrease. So this is not a complete. If I just try to increase the number of epochs. Into model, just going model, and here they have passed it. If I just try to increase the number of epochs and run it again, why it's not running? Epoch shifting model. Where is the function called? Why I cannot find it? The model they've given. Yeah, here. This same model and the epochs. Now, let's just give it some time. Till then, let me explain it. So basically, you already know class and simple model. So this is basically the OOPS concept by making class, and then we have constructor in it. Then we have basically we pass the input size and all and hidden size, and then we use step forward. So these are the basically the methods we use in basically what I say is the method, simple method, so simple method used by PyTorch uh, to make basically a function. Then we have a training function. So we have just tried to run a loop, and then we have optimizers config. Then we have changed. So here basically we have a train model. So we have just passed the losses train model, and we have fixed the outputs. And we just try to run it. Yeah, you can see that for 1,000 epochs, the losses which Adam gave. So Adam, you can see, like you were at the earlier stage, you could not find that Adam gave the most optimum solution by decreasing the losses. But when we just run for more epochs, you can find that Adam outperformed all other methods. The magenta line of Adam, you can see that it performed basically all other losses. So you can see say that Adam is better, and then RMS prop is also doing good. Adagrad is also doing good as you do witness prop. Momentum. RMS prop is little bit not going good, but Adam basically our Adam model is doing very good. So we can say that Adam is for now the best of it. So choosing the right optimizer, the general guidelines, Adams good default choice for most problems. Start here if unsure, works well across different domains, requires minimum training. And then you can just try with SGD with momentum, best for fine tuning and achieving highest accuracy. And then RMS prop you can try, and AutoGrad you can try, and then just leave these hyperparameter tips we'll be doing later on, but this is basically what how you can use like Adam, how learning rate you can fix, and basically you can read more about it. And the conclusion behind is that we have finally covered the day 7 lecture of losses and optimization. So this was our final lecture coverage of all this, and I will give you the notes of it. And here is another graph of Adam optimization. So we can also look by here also that although SGD with momentum performed all of them performed very good. So earlier it converged for like momentum converged very fast. And then Adam also, maybe it is late, but it also performed well. So the iteration number of iteration which Adam took is more, but it also performed very well. So you can look at the other graphs also. And then there is this graph like momentum. It is faster and it oscillates. So sometimes may happen that it may pass the global minima and reach to local minima. So you just go through these, try to run these code, and PyTorch will be taken care in later lecture how the things are working. I will be teaching you all that, and before that, you should just revise the earlier chapters, and this thing also you can just try using, like if I just try to run all of them together. See, Adam is coming slower, but it is coming, and then it will be converged. So it depends on the, if you just uh, try to change the, it settle down, and if you just try to change the different factors which are basically affecting the atom and other basically the factors, we will get the different values. So that's we do in hyperparameter tunings, and hyperparameter tuning tips are also given to you, which you can go through yourself and try to change the hyperparameter tunes to basically see what's happening, and you can just go to this formula and read it and check how these decay rates are affecting. So let's just wrap this lecture of our D7. So loss function and optimization techniques. So goodbye. See you.